Good morning. I'm back for another session of studying MIT's quantum mechanics class. Yeah, the project is nearing a conclusion. This definitely doesn't mean that I finished learning this subject. I was just thinking about this yesterday. There's two real things. Like I wanted to go into this with this idea that I'd try to get a foundation understanding the kind of basics of quantum mechanics, and I do feel like I've done that. Although, of course, that goal of like get an intuition about quantum mechanics is just so vague that like there's obviously like varying degrees to how well one can do that. So that's why I also picked this kind of doing this particular class and trying to get to a level where I could succeed in this particular class as a kind of benchmark for doing that. Without that, obviously, it would be kind of hard to even specify that. Now that I've gone through the class, now that I'm kind of nearing the end of this process, I think it's interesting to think about kind of going back to that original goal of getting an intuition and where things differ. So one thing I would say is that there are still, in my mind, some unanswered questions about quantum mechanics that I don't think I have answers for yet because I haven't gotten far enough. So meaning that they just weren't covered in 804. So one of those examples is that, for instance, these quantum mechanical analyses were usually done with a kind of generic particle, like assuming it's an electron or something, and just sort of saying, well, it's moving through this. Why does it have discrete energy levels in certain types of potential fields, and why does it, have band gaps in metals and solids and stuff? And so there's been a lot of interesting phenomena explored. Some of the things that I was most interested in was sort of trying to understand what is actually this kind of quantum mechanical picture. And one of the big kind of sort of sticking points for me is, one of the ideas of quantum mechanics, of course, is that you have some kind of wave function. So it's kind of as if particles and things that we're talking about, matter, are made out of some kind of waves that are like rippling, the way that we can think of as like sound waves or water waves or something kind of analogous to that. Except the difference is that, according to the quantum mechanical picture, there aren't actual waves, that the things are actually made of particles, and hello cat. And so the sort of challenge is rectifying this picture, that on the one hand you have waves, and on the other hand you have particles. And the sort of link between those two pictures is that the sort of physical reality is this wave function that is like a wave. However, when you measure it, it collapses, and it collapses depending on what you were measuring. So if you were measuring momentum, it collapses into sort of a momentum eigenstate. If you're measuring the position, it collapses into a position eigenstate. If you're measuring energy eigenstate, et cetera, et cetera, et cetera. And because it collapses into one of these eigenstates, and those eigenstates are mutually exclusive for each other. So if you have a momentum eigenstate, it can't also be a position eigenstate, that they don't look the same. That once it collapses in one, it also, by the uncertainty principle, kind of guarantees that you won't be able to find it in the other. So once it collapses into, all right, we're spinning in this direction, it can't have any definite spin in these other directions, just because the shape of the way the wave has to look in order to do this can't have these doing these. So I feel like I understand it. The key thing that was kind of, I don't know whether it was like, there's little bits of it being understood in this class, but I wish there was a little bit more exposition about what it means to measure something, because really this idea of like what it means to measure something is that it's a physical process. There's a physical process for doing something which causes it to collapse or causes it to, instantly change this wave function down to something. Because obviously, you can't perfectly tell where something is positioned, or you can't perfectly tell how fast something is going, or how much energy it has, or all these kind of things. So we're kind of squishing it, like we're kind of showing it in sort of one way or another. And so this kind of process, I feel like, was the idea of what measurement was not not done too carefully in this class. I feel like this class was a really good primer in the kind of mathematical structures underlying it, but I would have appreciated perhaps a little bit more of what it means to say that, you know, how do we know that it's a particle, for instance, as opposed to a wave? Like what is the apparatus for the experiment showing that? And so I've been kind of thinking through that stuff myself, but I don't feel like I received a super satisfactory answer. The only things I do know, which are not things that I have an intuition about, but things that, you know, I'm hearing other people talking about, are that it's wrong to think of them as just waves. So that was sort of my intuition is, well, why talk about, why not just say that it's this wave function and just the wave function just keeps going? Why bother with this idea that it has to be a particle? And that seems to be obviously the case that, like, if you have sort of a detector, you only detect it at one, like if you shoot off one photon, you only detect it once. You don't detect it like a little bit here and a little bit there. But of course, to me, that sort of begs the question of like, well, what counts as measuring? What counts as making it measured so that you would cause it to only be here and not have anything here and get that sort of probabilistic collapse? And so that's the thing that I'm kind of interested in. I know some people take issue with the unintuitiveness of something being probabilistic or this kind of thing. But for me, it's more a question of, well, obviously we're aware that there is, you know, contribution from this wave function. Like it interferes with itself. It has wave-like properties. It has interference terms. It has these kinds of things that are happening in different places, but that it has this kind of collapse sort of idea. And so I guess for me, the thing that did not get fully resolved in this class is that, you know, how does it count as collapsing, and like, how does that work? Because obviously, like the way that we've talked about in the class is like, suppose it was measured at this, but like for me, I'm thinking in my head, well, how did you do the measurement, or how did that happen? What was the physical process for determining that? So you could do that. And so I think that's something in terms of, I would call it entanglement and decoherence and these kind of things that would be something I'd like to investigate further. But I think I'd probably have to wait to maybe 805 or 806 to get into that a little bit more, just because I feel like a lot of this class was spent introducing sort of the basics of this system rather than all the possible intuitions. The other thing as well is that we're dealing with quantum mechanics, but we're not yet at quantum field theory, which merges special relativity. So special relativity is just the whole idea that things only move at the speed of light, and so quantum field theory, if I understand from an outside perspective, is the idea that instead of viewing things as particles, you could view it as an entire field, and these fields are interacting with each other. And so that also maybe helps explain a little bit this symmetrical particle idea, or this identical particle idea, is that if you view the identical particles as being somewhat separate objects, then that itself can be kind of like confusing. Well, why does it matter whether you can swap them or not? Whereas if you view them as being kind of excitations on one kind of field that fills all of space, then that gives it a bit of a different impression, I guess. But having gone to that, I would say that there has been a lot of things that I feel like I now understand satisfactory, like why are energy levels discrete? Why are there atomic orbitals? And it's just because, kind of the same way that if you blow into a bottle or something, it makes a particular sound because the wavelength of sound has to fit in that jar to be resonant. Well, there's a kind of similar, although even more extreme version of this when you have, you know, a hydrogen atom sitting that is this kind of has a certain frequency that it can sit at inside of the potential. Otherwise, it won't fit. It won't sit in there. And so hence you have these discrete levels. I also feel like I've got a better sense of what superposition is. Superposition was always sort of explained as a kind of mysterious process. But when you think about it in terms of a wave function, like superposition in terms of waves, obviously it's very complicated. But if you pass two waves through each other, that's basically superposition, right? And so I think that in thinking about it in terms of, okay, well, what is it in terms of a wave? So you're just taking one wave and you're adding it to another wave. And just the idea of this superposition is because these are linear operators. If you have a wave moving like this, and it has whatever shape, you know, wave moving like this, and it has whatever shape, then they kind of pass through each other. They're just not a sense of that because they overlap, they do something funny, and then the waves get destroyed. So that means you can have one state that looks like this shape, one state this shape, and you just overlap them. And it's kind of like it has both states in the same space. But if you were to draw it as a wave, it doesn't look that crazy. It's just, you know, it's just overlaid on top of each other. So that superposition, I think, obviously it's more complicated when you're dealing with 3 dimensions and things like that. But it's not, I don't think it's as crazy as it sounds. I think the thing that is crazy is just that this is a probability, so it has to collapse down to one of these eigenstates. So I think that was the part that, for me, I would like to explore a little bit more, is sort of, you know, we're associating these operators with measurements, but obviously a measurement is realized through some physical process, and it has some uncertainty itself. And so the question is sort of like, how does that affect this, not really how does that affect this collapse, but what would count? What kind of physical process would do that thing that we're looking at? So that's sort of interesting. I think I definitely feel like I've got a much better understanding of this if I wanted to go do quantum computing. So that was one of the things that I wanted to learn this for, was to understand quantum computing, because obviously I've done a lot of studying for computer science, and I wanted to do more of that. I wanted to do quantum computing potentially. And I remember listening to the first lecture of quantum computing, and I was like, I don't get this. Like, what do you mean, like, you have it in a superposition of this? It just sounded kind of crazy. And so for me, I definitely feel like, okay, I get that now. So if I were to take a class in quantum computing, I think I definitely have enough to understand quantum computing if we're not talking about like the physical realization of these systems, if we're just talking about it in terms of computer science theory. So that's sort of interesting, and I'd like to maybe explore that later. So I've got a lot more to learn after this. This is definitely not an end point. It is the end point of my particular challenge. So, you know, come 1st of May, I'm going to stop doing this, and I have to get back to work on other things and other projects. I just cleared off this month of my time. But I think I'm probably going to keep, maybe I'll start looking at 805, 806. I'll start maybe looking at quantum computing classes, might work on those for a bit. And then we'll just see. I might be a little bit of time, but I might get back to doing sort of a project like this. In terms of this sort of project, doing it live streamed has also been interesting for me, because I you know, it's funny, like there's not a lot of people watching. I've got a couple people watching right now, but you know, so in terms of like when I write articles, I'm sending them out to thousands of people and stuff. So doing something for hours and hours where you only have a couple people watching is not usually the goal of what I'm doing when I'm writing or producing things. But at the same sense, when I would do these projects in the past, no one was watching. There wasn't anyone watching those things. And so part of the reason for me for doing these things in the first place was not only just so that I could learn how to do it, so I could teach people better, but also I like to do these projects like the MIT Challenge Year Without English just on my own. I like doing these challenges. And so this live streaming has given me a real new perspective on that. One of the things that I would say that it's changed is that when I was doing the projects by myself, it kind of made sense to do them short time frame, very intense, just because it made a nice, neat little package to discuss the project for. If you spread it out over a really long time, it's a little bit harder to document. It's a little bit harder to kind of say anything concrete about it. Whereas if you say, okay, I only did it in a month, then you kind of have this short time frame you can work for. I only did it in a couple months. But because this is, you know, live streamed, and so there's video and it's kind of happening continuously, it has made me rethink what I would like to do for live streaming. So I've thought about, you know, this was a lot of hours put into one project in a short period of time, but I could imagine doing, you know, shorter projects that are kind of just like an hour a day live stream. So I have to kind of decompress after this is all done and sort of decide what I want to do, whether I want to do another live stream project like this in the future, or whether I want to, you know, do a little bit every day or something like that with the various things that I'm learning, and just kind of share that process rather than just do it privately. But anyways, it's been an interesting process. I found these very interesting videos of Feynman talking about quantum mechanics to a lay audience, so giving like a lecture on quantum mechanics. And it's kind of nice. I wish I had gotten them earlier in this program because they're very interesting. So even after I'm done this course, I'm watching some of these videos. And it's very interesting to see how he tries to explain it without using math, because obviously the math is very challenging, and that's a real obstacle to understanding this. And it was interesting for me to see how he's explaining with math and how he was able to make it even simpler than how I was thinking about it in my head. So my idea in my head is, well, you've got some wave, but don't think about it as just a wave going up and down. It's actually rotating like this. And so his idea was to like get rid of the whole wave picture, just have one point, just have one arrow rotating, and then it's rotating in time. And I thought that was very clever. So I'm sort of watching a little bit more now. Maybe he'll explain some of the things in a non-mathematical way that I'm struggling with, like namely like what counts as measuring something, or what is the sort of scientific justification for why you can't just consider them waves, why you have to consider them particles, or like what's the, you know, what's the understanding of that. So I would like to explore that a little bit more. Right now, though, I should probably get back to questions. I should probably stop ranting and dilly-dallying on this one. So let's look at where I'm at. So if I recall correctly, I think I was on 10.4. Did I finish 10.4? No. Oh, I had started 10.4. Ah, right. Okay. So this is the identical particles question. In terms of my second pass of the problem sets, I'm nearing the completion of that. I've got 4 more problems here to do, although 10.7 is quite a long one. There were some additional ideas I thought I would review. There was additional ones that I thought I might do a third pass for if I have time, although it's Friday today and I wanted to switch to doing some sort of exam prep, so I might not have time. So what I'm going to do now, switch over, work on these guys. I'm going to try to work on these throughout the day. I think if I get done, I don't think I'm going to do any more Feynman techniques. I don't think I'm going to do any more of these problems. I think if I have time, what I'd like to do is look at maybe one of the exams. Now, I have to check how many exams I have. I know I have midterms and exams without solutions for more than one session, but I only have ones with solutions for one session. So my initial plan was to do on Monday, do midterms and exams that I don't have a solution for, and then on Tuesday do them for one that I do have the solution for, so that hopefully I might be able to get some kind of evaluation of, you know, how well am I doing in this class. Definitely, if I had been getting all the problem sets right, I wouldn't feel like that evaluative step is super necessary. But I mean, I got most of these problems, I got them wrong or like needed help during the learning process. So these were very much learning materials as opposed to evaluation materials. Hold on one second. I would like to have something that I can evaluate myself on the end of this project. I don't know whether I'm going to be able to do that with this exam. I've been sort of mentioning throughout the class that it's from a different session. I don't know whether that's a big deal. Like obviously if they cover the same material, it shouldn't be a big deal, but sometimes they don't cover the same material. So there might be a couple questions that have to do with something I didn't study, which always makes it harder. Or they just focus on, you know, they did different problem sets. And so this is like, as you did in the problem set X, but I didn't do that. So I don't, you know what I mean? So there's sometimes that can happen. I find that the more standardized the class is, the less of a problem that is. And also the more, the more challenging the class is, the more of a problem it is. So for this class, because it's quite a challenging class, the switch between sessions might be harder. If I was finding the class quite easy, then even if the sessions were different, I might have understood it at a very high level so that I could still make sense of it. But I've been working on it really hard. You kind of build understanding up like this, and I've gotten some way up the pyramid, but not all the way to the top. So it definitely will be challenging, I think. So, all right, I should probably stop wasting time and get over to doing these questions now. All right, which one am I doing? 10.4 all? Okay. Oh, right. So, okay, we just did the distinguishable case. So now let's maybe do the symmetrical case. So let's just go psi s. And we want to calculate x1 minus x2 squared, which is equal to x1 squared minus 2x1 x2 plus x2 squared. And so that is going to be on our psi s x1 squared minus. Oh, thanks, JC. All right. So I want to write this out carefully. This is going to be a real big messy thing. So should I just write the whole thing out? Yeah, I probably should. Okay. It's so big, it's very easy to miss things. And you have to be very careful about what you cancel. I was canceling things inappropriately last time. So I was like, oh, it's just odd, so it doesn't count. And you're like, no, but there was an extra x there. Ugh, all right. So we have, so I think we can just take the 1 over root 2 out, because it's going to be multiplying, so it's just going to be 1/2. So I'll just put the 1/2 out here. And then we have so I'll just do size first. Psi 0, x1, psi 1, x2, plus psi 0, x1, psi 1, x2. And then we have in the middle, we have our x1 squared minus 2x1, x2 plus x2 squared. And on this side, we have the same thing. These are all real, so we don't have to do the complex conjugate. 0, x1. Oh, I'm already screwing things up. This is x2, x1. Honestly, for some of these problems that are so big, there's a risk of me just making transcription errors. All right. All right, so we'll throw a dx1 and dx2 here. So this is actually double integral. I should make that clear. So let us now I'll do dx1 here and dx2 here. And so let's multiply everything out. So we're going to have 4 terms, I think. We have our, well, let's just do it here. So I'm just going to put the x1 squared plus or minus 2x1 x2 plus x2 squared here. And then let's just multiply this out. So we're going to have psi 0 plus this guy all right. But then we're going to also have it over here. So there's going to be 2 of them. And then this one here is going to be plus x2 squared All right, so we can now separate these things out. So let's consider 3 parts. So we'll go, I'll just call this 1, 2, and 3. So 1 and 3 should be the same from our last case. So, well, 1 is the same from our distinguishable case. So this one should be, you know what, I'll do it again just because I did make a mistake when I calculated it the first time. So let's do this 1. And then this guy is 1 over rho root pi e to the minus all right. That's our 1. This is x1, this is x2. So we're going to kind of integrate these separately, I think. So we're going to have x1 squared. So this x1 squared term, let's do that one first. Oh, I'm forgetting the, excuse me. So, for these guys are going to just cancel, right? And then this is going to be x squared. So for this one, so this is, I'm going to call this A. Oops, I'm doing the wrong way. A, B, and C. So for A, this is A. So we're going to have an integral of a quadratic and a Gaussian, which this should be squared. Right? Yeah. So if I'm not mistaken, what happens when we get a quadratic of a Gaussian? We should have rho cubed over rho cubed root pi over 2. Is that right? I have it on my flashcards here. Yeah. So that's going to give this coming down here. And then I guess, yeah, I'll just evaluate. I'll leave these halves out because the halves on the outside here. I'll just leave the half out, integrate back in the half after. And then let's do B. Now B, in this case, is going to be minus 2 x1, x2. So I can just, I'll get this one here. X2 squared over rho. No, because these things are multiplied. Hold on a sec. Oh, but I think this is going to cancel off this here, right? Because when we're doing this integral, no, that integral is 0. What about those rows, though? Oh, this is the thing. I try to make simplifications and I make mistakes. Let me just write this out first. E to the x2 squared over rho squared. All right, so in this one here, if we integrate here, if we integrate over x2 first, that'll make these guys 0, right? Not 0. Shouldn't it be when we evaluate this we get 0? Why don't we get 0? Because when we evaluate this integral, this is an odd function, so this x2 looks like this. And it's odd, so it should be 0. But we don't get 0, we get this. What am I missing here? No. This is what I'm forgetting. This is what I did last time. Squared. Right. Okay. I forgot to square this term. Yep, that's what happened last time too. And this is rho squared. Okay. Now we're back in business. So this guy is going to be pi cubed pi over 2 times, this one here is also going to be pi cubed same thing, but we're going to not have the, so I'll just do it here, root pi over 2, and then we're going to times this by 1 over pi root pi times 2 over rho root pi. So we have 6 rows on the top, cancel with 4 on the bottom, so we're going to have it equal to rho squared. We have 4 divided by 2, so we're going to have 1/2, and 2 cancels, so we get rho half. And is this negative or positive? I believe it's positive. Okay, so there we go. Oh, that pesky square. This is why I get these things wrong. I forget to do them. Okay, so this is going to be, so now we're doing b, which is x1 times this, and this is x2, but we have squared. This is cubed, right? this one is only odd functions. So this one is 0. And if we consider C, C is going to be x squared. So it's going to be minus 2. Oh, no, oops. What am I writing down here? I'm going to have this 1 over root pi e to the now this is to the 4th. So we have x2 to the 4th rho squared times this one I don't know offhand, this integral. We can do this regular Gaussian should just be rho root pi, so this should just be rho root pi times 1 over rho root pi times 2 over rho root pi times whatever this integrand is. So what is that integrand? Go to my favorite page on Wikipedia, Gaussian integrals. So if we have 2n plus, okay, so this, if we have n equals 2 now, so x to the 4th, we should have what? Which is going to be, so we should have a root pi times a to the 5th. So this is rho to the 5th. I mean, that makes sense, but that's not going to give me the answer that they had for that one. Well, we do have a rho squared here. Hold on a sec. So I'm just going to also put times. Rho to the 5th, 2n minus 1. So that's 4. 3 factorial is 6 factorial. Ugh. Oh, no. This is a halfway integral. Shoot. How do I do it for negative infinity to positive infinity? It's just going to be double this. So let's go 6 factorial is what? I should know this one. 720. Divided by 2 to the power 3. We have 8, but it's going to be twice this, right? So it's only going to be 4. No, this is definitely not looking right. Hmm. Why am I getting this to the fifth? It's supposed to be the same order as this other one. I'm missing something that would cause this to change. Maybe not. Hold on a sec. So we have these guys are going to cancel. These guys are going to cancel. 3. So still looks like the right number of rows. So 1 cancel 2. So we're going to get row squared. But now this isn't right. I've got 1440 divided by 4. Like it's way too big. I'm missing an additional scale factor somewhere. Because this is saying I've got 14, 4, 7, 20 divided by 2, which is 330 plus 10. So this is saying 360 row squared. But I know it's 3 halves. What am I doing wrong here? Like, I'm assuming Wikipedia is not wrong. Three factorial 6, 6 factorial 720. I should know the double factorial. Oh, wait. I don't know the double factorial. Is the product of all integers from 1 up to n that have the same parity, odd or even, as n? Oh. Okay, so this is not 720. What is this? So this is 3. So it's just 3? Okay. Hence our 3 halves, which is what we wanted. So 1 is going to be equal to 2, which I mean is what we expected given the whole answer to the first question. All right. Well, good to know. I learned something new. I learned that double factorial doesn't mean do the factorial twice. Okay, I'm going to just get some water. All right. Let's move forward. I want to go now on to part 2, which is, let's do 3. Let's do 3, which is going to be just the opposite of this one. So 3 is going to be the same as, so if we look here, 3 should be the same as 1 because these are just switching the variables around. So this one should also be 2, right? And so if I cancel the half here, I'm going to remove the 1s here, and I'm going to remove the 2 here. Okay, so let's do 2, which is going to be all these cross terms. So same as 1, and then we're going to have 2. It's going to be equal to what do we have over here? We have theta 1, theta 0, x1, theta 0, x1, x2, theta 0, x, theta 1, x1, theta 1, x2. So we've got this. So what is this integral going to be? So let's again do A, B, and C. Break it into parts. So let's do A. It's going to be x1, x2, x1 squared times. So we're going to have, let me go to the problem set. 1 over rho root pi. Actually, I think we can get rid of the 2's because we're going to get the contribution from the second one. All right. Because we've got x1, x1, x2, x2. Okay. And then we're going to have from this, instead of, it's going to be x1 over rho, x2 over rho, as opposed to our x squared. And what's this going to be? Well, this is now odd, right? So we can just go cubed. So this one's odd. This one's odd. So I think we can just say these equal 0, and we just only have to consider this b now. And then we write this again. So you know what, I will just put this. All right. So now we have just two Gaussian integrals multiplied against each other. So let me write down all the constants. So we're going to have minus 2 pi times 2 root pi. Now we have, just go from these guys. Cancel those off. And now we have the first squared, which is going to be rho cubed divided by 2 root pi. And then the second one, which is going to be rho cubed root pi divided by 2. No? Is that not? That should be right. Yeah, because we do it first in this and we get this out. Then we do the second, we do get that out. And so now we should get again rho squared. And these should all cancel except for a minus sign. So you get minus rho squared. So going back up to our thing, we have rho squared minus rho squared plus rho squared. It's equal to Oh. All right. So this is what we expect. Now let's do the distinguishable case, which because we've done a lot of this work should be a lot easier. So now we've got minus signs there. So how does it look if we've got minus signs? Well, these two guys don't change, so they're going to be the same. So we're going to have rho squared. So I'll just go, 1 is going to be the same, equals rho squared, and 3 is going to be the same, equals rho squared. And then this central guy is going to be just minus this. And we're going to have the same issue here where the A and C is going to be 0. So it's just going to be minus minus. So we're just going to add this. So it's just going to be those 3 rho squared. All right. Wow. Got to be very careful with those integrals, but I feel like I got it. Hold on a sec. I apologize. I've been so congested this whole month. You just got a whole month of me blowing my nose. So a couple questions came up. Katya is asking, do I think that some people need less than 8 hours of sleep? No, actually, I really recommend a book called Why We Sleep. The author, his name is escaping me right now. I should have it somewhere here. I can't see it right now, but if you just Google Why We Sleep, they talk about, they've done research on this. There are people, it appears, that have some genetic variation that allows them to sleep for much less than other people do, but it's exceedingly rare, like 1 in like 10,000 or something. So for the majority of people, they think they can do it with less sleep, but that's not actually true. Do you think you can use ultra learning for music? I mean, I haven't used it for that much music. I have used it for visual arts before. So I did a portrait drawing challenge. I don't see why you couldn't use it for music. I don't really have, I haven't encountered an area which, to my definition of ultra learning, where it doesn't apply. And that's also kind of by design, because how ultra learning works is that it's sort of just designed as like effective, kind of aggressive, effective learning. The only places I think that you would maybe want to be careful applying ultra learning is areas where the risk of physical injury might be high if you don't have that. So it's possible for some kinds of sports. I mean, some people were asking me about ultra learning martial arts, and I mean, you could do that, but I would just be more worried about injuring yourself by kind of pushing yourself too hard. But again, it really depends. The ultra learning itself is kind of a slippery concept. I've struggled to kind of define it in a way that's consistent across all things. The definition that I've stuck with, which is a little too broad because it encompasses two things, is self-directed aggressive learning. But I mean, that can describe a lot of things. So I tend to think of ultra learning as just more a philosophy towards learning. But then, of course, it breaks down into much more specific principles. So I've written a whole book about trying to break that down into specific principles. So I think once we talk about specific principles, then those principles tend to apply, but they tend to be not just the entire act of learning, but one aspect of learning. So I guess I will move forward now with part C. Plot the probability. Oh God, this thing, because I got this wrong. All right. We associate with the three wave functions as a function of x1 and of x2. So I think the right way to do this is a contour map. And I think and this is going to be our x1. So last time I tried to do a 3D graph on paper, and it's like super challenging to draw, and I was getting it wrong. So in our distinguishable case, what do we have? Well, we have psi of x1 is just our Gaussian. So I'll just make this equal to 0. And this equal to 0. This is just a Gaussian. So it looks like that. And this guy here is a Gaussian with an x term. So it looks kind of like this, I think. Right. So our joint probability distribution is just going to be these two things multiplied by each other. And so I'm just going to plot the peaks out first. So the peak, this is a minima, and this is going to be a maxima, and this only has a maxima at 0. So what does this look like? Well, and And this is also going to be a 0 point. So this is going to be a maxima. Let's make a maxima. And this is going to be a minima. This is going to be 0. And what's going to be happening here? We're going to have, this is going to get lower, 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 and here lower, 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 and here it's going to be sharply lower. So we're going to go kind of like and that's probably enough. And let's draw, well, maybe I'll just do some hatching for the kind of even case first. I should maybe do this in color, be a little easier to draw. All right, and then these guys are going to be positive, so I'm going to make them lighter. And these guys are going to be, I'm going to make it a little bit more spaced. This guy even more spaced. And then I'll just shade this guy in. And I'll just make a height here of like that. Okay, so this is our distinguishable. Now we want our size symmetrical. So, excuse me. When we add these on top of each other, what do we get? What does it look like when we add these two together? I don't think it goes negative anywhere, does it? Did I do that right? I don't think I did this right. Oops. Because this isn't a negative, this is also a positive, I think. They're added together. And it's difficult to draw these things. So now the symmetrical case. So this is just the averaging of them. Right? So this is just going to be this. I think this is still the case because I think this is sharper. I think I drew this kind of wrong. I think it should actually be more like this. Because to be properly normalized, I think this has to be sharper than the other one was. So it is plunging down. But it'd be plunging down even more here than here. Ooh. Yeah, I don't think it looks like this. So, oh, right, because, of course, the probability. We're doing probability, so it's going to be these guys squared. So it flips around, right? So this is, you know what, I'm going to do it the opposite way. And then I'll just erase this. There we go. All right. Now, what do I have here? In this case, we've got this, and we're going to add what to it? We're going to add this guy. So I got to make sure that this is exactly in the center here. So this is going to be plus. It's going to go down a little bit and then out again. And this one's going to go up a little bit. It's going to go up more. Right. So if we're adding them together, no, they're multiple. This one, it's an average of the two. One sec, let me just write out what is. Try to, so psi s of x1 is going to be 0, and we're going to have. So let's just do the x1 part. So it's just going to be an averaging. So we're going to have this. Plus this is going to be something like this. Forget how this is scaled. You know, I'm gonna graph this just because otherwise it's gonna be. I'm missing all the factors here. So let's go. Let's say row is just 1. So we're gonna have I don't think I need the root pi either. We can just leave that the same. So this is just going to be a factor of 2. So we're going to have e to the negative x squared. Oh. E to the negative x squared. What does this look like? Plus 2x. Oh, yeah, no wonder. Okay, here. Okay. So I get getting the right kind of shape, but something like this. And so our probability is going to be a little peak. I think this is 0. So we should have that, right? So here's going to be our minimum. And we're going to have a little height here. This is a little bit. And then the height is going to be more like here. I feel like, oh, there's a second row there. Shit. I mean, if row is just 1. Change the shape? Not really. I feel like this should be centered, but oh well. And this is going to be like, I guess this isn't quite as dark. And then what's our anti-symmetric case? Well, our anti-symmetric case, we have this minus this. And so it's going to be one side is going to be like that is going to be one side, and the other side is going to be like this, right? So we're going to have something like this. So you're going to have a little maximum here and another maximum will be below this axis. And this is one's going to be over here. It's supposed to be 0 there, but it's not. What am I doing wrong? Let me try again with her. Because I think the symmetric one I'm doing wrong too. All right, let's just go like this, like this. So our psi s squared, we've already decided is our psi 0 squared squared. So this is the distinguishable case. So that's going to be, we're going to have 3 contributions to this. So we're going to have our distinguishable case. So let me go let's go on the x1 line. So this is going to be x1, and this is going to be x2. This one here is just our Gaussian squared, so I can just go like this, Gaussian. And we also have our this thing squared. And then we also have a contribution from, 1 second. And then we're also going to have a contribution from these two guys multiplied together. So let me just graph that right here. What does this one look like? We also have two of these ones. So when we add them together, it should look like no, where did my x union x squared? Shape does this have? Yeah, it is that. So we square this. Hold on a second. Or am I wrong here? Oh boy, there's so much stuff going on here. Right. Because this is going to be x squared. Hold on a sec. And this one is, but this one only has one x term. Yeah. Right. So this is like something like that. And then if it's minus, then this is becoming minus. Definitely put the terms on the wrong one here. This one's 2. they should be symmetrical, and I'm getting this weird this weird pattern. Because I think the distinguishable case is like this, where you've got and this one's like this, kind of like I think it's because I'm trying to square them separately. Yeah, that's where it's causing the problem. Yeah, so what I need to do is draw these graphs, not the squares of the graphs for each one, but I need to draw the amplitude in each direction and then square it when it gets to the center. So if we're talking about amplitude, what do we have for symmetric? Let's consider so that's going to lead to like that in the symmetric case. And then in the asymmetric case, it's going to be minus this. So we're going to have, let's say like this. And then this one is like, so these cancel here, and we're going to get a something like that. All right, D. Suppose a lab partner places 9 identical bosons of mass mu in an infinite square well with L cooling down lows. What is the wave function? So it's going to be N E naught N E naught or N phi naught. So the energy in the infinite square well is what? It's what was the spacing in the infinite square well? Omega L. formula sheet. Oh, here it is. Ah, okay. So it's going to be n is 0, so we're going to have pi by L squared. So this is equal to h UL squared. And so the minimum energy is going to be pi by L squared h bar squared over 2 mu. So this is the amount that you need, the minimum you need to excite. It's just going to be n of these. And then for fermions, of course, it's we're at the nth state, so this is how much we're going to need to add to excite it. And then it's going to be just the sum of, yeah. N of all right, I think that's right. Let's look at these graphs now. So I think this is the thing that I was doing wrong, is that this is like symmetrical this way. And I've got it asymmetrical, and it must just be me adding the factors wrong. Because what is it going to be? It's going to be x1 and x2. So we're going to have like this. All right, I'm gonna finish off that one. Now I've got 3 more left. Let's do 10.5a now. Now will probably be a good time for a flashcard break. This is going to be a root pi. This is 0. This is a cubed over 2 root pi. This is sine h. LZ in spherical coordinates is h bar d phi minus I h bar d phi. Lx is y pz minus py z. Y pz minus z py. Oops. This is L over root 2m v naught over h bar. Yeah. Kilograms meters squared per second or joules seconds. As exponentials is e to the kx minus e to the minus ikx divided by everything divided by 2. This is e to the kx minus e to the minus kx divided by e to the kx plus e to the kx. Just the energy in terms of these, so it's going to be a plus a minus plus 1/2 all times omega h bar 1 over root L or root meters. This is h bar m while m. This is going to be xpz minus zpx. Oh, it's zpx minus xpz. Oh, interesting. Okay. Okay, yeah, I have to remember this one because it's the opposite of the normal order. All right. Cosine h in exponentials is e to the I kx plus e to the minus I kx all divided by 2. Wavelength of lambda. I don't know whether I've got this question wrong, so let me just work it out here. H bar omega. So this is mv is equal to h bar omega. Omega, though, is equal to c divided by lambda, right? So we have, oh, but the v is the c. All right. No. I don't know why I'm screwing this up. This is like such an easy calculation. I think this is one of those things that I'm like messing up just because I don't focus on it. P is equal to h bar k. K is equal to lambda over 2 pi, or is it 2 pi over lambda? You just divide it by 2 pi. Ergo, mv is equal to h bar lambda over 2 pi. Lambda is equal to 2 pi mv over h bar. Okay. Something is wrong. What is... I don't want this. Okay, good to remember. All right, this one here is h bar squared L plus 1 while M. This guy is xpy minus pxy. Ypx. This is just minus I sine I kx. And integration by parts is u integral v minus integral u prime integral v. Okay. All right. Have some things better memorized now. So let me just erase this here and get back to questions. Oh, right, this guy. Okay, so all right, show d dt h bar q is equal to f. And what do we have? We have vg and we have dE dt is equal to dE dx is equal to force. What else do we have? All right. Now let's go back to so we take everything here, ddx. So let's go ddx of vg chain rule here is going to be To remind myself how to do these things. Okay. Let's rewrite in terms of the little deltas. That's going to make it a little bit easier for me to do. So we have Let me write it out again. H bar Q dt is F. This is what we're after. And what do we have? We have the E dx of F. Hold on a sec. Maybe I won't put these in, just so that I can keep it clear. I have dx dt d squared dx dt squared x times mass force. What else do I have? I have dx dt is equal to 1 over h bar dE dq. All right. So I'm going to have dq dt is equal to 1 over h bar dE dx times h bar, so dq dt h bar is equal to the x, which is equal to f. There we go. All right. Let me just double check that 5a. 5a, oh, here. Okay, so I can cross that one off now. Oh, 10.6 I never did, so let's do 10.6 now. So Deepak is asking, how do you learn coding effectively? I want to learn to master Python and scale up, but I keep forgetting the syntax. So there's two ways you can do that. One way is you can actually go out and make flashcards, basic space repetition stuff. You learn the syntax, you memorize it, you practice it. That's a good way. I tend not to do that. because I find it's usually the case if you just do a lot of programming and you try to remember it, you don't remember it, you look it up. You try to remember it, you don't remember it, you look it up. Like this will be its own kind of spaced repetition. So generally what I do is I don't worry too much about memorizing the syntax. I just try to use Python a lot. So do some project, do it. And whenever you don't know something, you look it up. Obviously, you want to try to recall from your head, but if you forget how to do it, you can look it up. I don't really worry about memorizing syntax too often. I think you want to have some examples that you go back to. So you learn how to do something and then you're like, oh yeah, I did that before. How did I do it that last time? So you can look it up. I think the main thing you want to remember when you're learning a programming language is you want to remember how it works. So what are the concepts? I think that's more important than just mastering the syntax, because if you know, okay, I know I want to do this kind of thing, then it's easier to look it up. But yeah, if you want, you can also use spaced repetition systems. So let's look at 10.6. Sketch VG QL and M not QL for QL. Less than pi in the first two bands. I think I did do this one. I don't know why I'm saying it this. So let's just move this one on, because this one here, I think I just did it qualitatively. I didn't actually sketch it out. So let's just move on to the last question, which is also super involved. 10.7. Oh yeah, Matan is right. If you are doing a written exam, you probably want to memorize. Now, I want to be clear. What I'm saying is not that by looking things up, you won't end up memorizing things. It's just the question of how are you memorizing it. So one way is to separate it off and put it into a flashcard program and memorize it. This would be what I would call like a drill. So if you're really finding memory to be a bottleneck, you might want to be doing a drill. On the other hand, you could just consider learning the syntax by memorizing it through doing it in context. And the advantage of that is that each time you are exposed to, oh, right, how do I write this? You are giving yourself a bit of a spaced repetition for that particular factoid. But the thing that's important here is that because it's through a natural context, the frequency with which you test yourself is going to be proportional to how often the syntax comes up. So if it's something you have to do frequently, like if you're doing Python, I'm always finding like defining a function is just like, that's baked in because you have to do it all the time. Whereas if it is something, like the syntax for regular expressions, okay, maybe you don't do that as often, so you don't practice it. So now to go back to Matan's point about what are you going to have to memorize? Well, if it's an exam and you can't look things up, it's going to be the syntax that you don't have to do that often, so you don't have that many repetitions of looking it up, and it's quite memory involved. So regular expressions would be a really good example of that. However, if you do a lot of programming, you will probably, just by doing it, memorize quite a few things. So again, it does depend on your purposes. So if you can't look things up, you may want to spend time memorizing things that require a lot of memory, but you're not going to get a lot of practice on. Even if you're doing it in the real world, you might want to practice. The one thing I would say to just be careful about is that if you just immediately go to look up, you don't try to recall when you do it. So you don't treat it as a little bit of an active recall situation. When it comes up, then you're not going to practice it as much. So you maybe have seen me doing this when I'm like, oh, right, what is that? I try to figure it out first, and then I look at the notes. And the reason for doing that is that I'm trying to put it into my memory rather than just having it here. But really, when I encounter some question of like, oh, right, what was the Schrodinger equation? It is a little bit like it's happening on a flashcard. Like I have to recall it right now. It's just that it's come up in context versus separately in a flashcard program. So I don't want to say that memory isn't important. It's very important for programming. The question is how to memorize it. And in some sense, you can choose to go with a drilled approach where you kind of isolate everything off into components and you practice it all evenly, or you can use a sort of in situ approach, or like doing it through the actual practice of using the skill. And the two have different trade-offs. So If the memory is really your problem, you might want to break it away from the programming and work on it. There's different reasons for doing that. But as Matan mentioned, if you're doing a written exam, there might be certain things. Regular expressions are the thing I keep going to, but regular expressions, because there's so much little syntax to memorize. Okay, how do I get it? So I want numbers, but I want this and want that. And maybe you only write a regular expression like once or twice in a program, if you're not doing a lot of text parsing. So that's the thing that I'm always having to look up. Like I never remember the regular expressions. But on the other hand, I'm not doing that many tests that I have to do regular expressions on a written format. So it doesn't really matter for me. But a lot of other things that happen all the time in programming, you will also memorize them when you are writing programs. All right, so back to this question here. So show that this condition on Q and E together with the definition of scattering phase above leads to blah. All right, so maybe I should just look through this again here. All right. Okay. So what do we have? We have cosine of QL is equal to t squared minus r squared over 2t e to the ikl plus 1 over 2t e to the minus ikl. And we want it, hold on a sec, our t root t e to the I phi, and we have r is equal to root r plus or minus, hold on a second. And where is our definition? Scattering phase, phase shift. I don't think it's in here. All right, so this is one of those questions where I have to just plug it in, I guess. I put it here, so I definitely got it wrong last time. So let's see if I can do better this time. So this is going to be, I'll just put, so we have t, the I, 2i, I. So plus or minus 0 plus or minus up here to match. Hold on a sec. Where is it? Where is it? So let's just flip this around. Minus plus r to the minus 2i phi. And this guy is root t All right, let's get it all together. We're going to have root t e to the I phi divided by 2 minus or plus r over root t. So we have t plus r is equal to 1. So r is also equal to 1 minus t. So we can go plus or minus. Minus 3 I alpha all right. So let's just go I plus k. This is going to be minus. This is going to be let me rewrite that up here. So I'm going to have root t over 2 e to the I do I want to split this apart? Sure. So this is going to be 1 over 2 root t plus or minus e to the minus I. And I go I, I just leave it as positive in all cases. So I KL minus 3 5. Yeah, I'll just go I And we're trying to get into divided by this root t. This looks like something I can turn into a cosine. Right? So let's group so we have root t over 2 e to the I equal kl plus I. And then I have this one here, which is plus or minus root t over 2 to the I kl minus 3, 5. Then I have plus over 2 t e to the minus I kl plus I. So if we take the top plus ones, so this is going to be top. We have root t over 2 how does this? These are not the same phase. How do I factor out a phase when I'm adding the cosine? So if we add these two together, we got t we do the ones that match, we get I'm trying to think of some trig identities that might help me with this. Something's supposed to cancel and I just didn't look at it properly. Like this definitely lowers one here and raises one here. Ooh. I'm trying to cancel off here. Hold on a sec. T squared minus R squared. Give me T minus R. Divided by two e to the I5. I'm forgetting the complex conjugate here too. So we get cosine this t minus r. T minus r is going to be t minus r is equal to 1 minus t. 1 minus t. So these are going to cancel, right? And we're going to get cosine KL. So much easier than what I was doing. So the key thing I can't forget is I'll put key to remember. The complex conjugate, is that what we're doing here? How do I justify doing the complex conjugate though, as opposed to just squaring it? Let me look at the answer here. What is this? 7, 6, 7, 8. So what do we have here? We have t squared minus r squared t e to the I2 phi r. Here we go. And so it was 1 over 2 t minus 2 I2 phi e to the IKL plus e to the minus IKL. IKL. So this wasn't right. I'm not supposed to do the conjugate, but the thing that I missed ooh, this was minus as well. Was that the case up here? Yeah, it was. This is a copying error. Shoot. Yeah, because that would have all subs canceled out if I hadn't forgot that minus sign. Oh. Transcription errors. Wow. All right. Let's go back. Let's do part B now. For Vx, a generic potential, explain why there are no solutions to the equation derived in the regions around K. Specify n pi for any integer n. That's because cosine QL equal to for n pi. So that's this is strictly less than 1, therefore whole thing. No solution. Supposing dx is very weak, then t very high. Width gap shrinks. D. Let's do the actual calculation. Show that this limit the area gaps with the width of the gap around approximately given by gap is equal to root r. Okay, that's an interesting question. All right, so we have the gap is going to be cosine KL What's the right way to frame this? This is the gap, right? No, it's and cosine K1 K2 L minus I root T is equal to 1. K squared is going to be K plus epsilon squared minus K squared we're going to have K squared plus 2K epsilon plus epsilon squared I think for small epsilon we can probably ignore this. Is that the idea? Oops. So we want this to be equal to 1. What's the right way to phrase this? So let's go with cosine minus I is equal to root T. So K1 L minus I is equal to root T. And we also have K1 plus epsilon L minus I is equal to there's some small angle approximation, but I'm not sure what it is. Oh, we can just match these though, right? We can have K1 L So we're going to have two different values. So let's just draw our circle here. So if we can imagine cosine being one here, we want it to be here and here. So this is going to be at root t cos inverse. Root t is going to be cosine inverse of root t plus 2 pi, right? Almost. What's the right way to do this? How do I measure the width of this gap? Oh, I think maybe the idea is that for small angles, is this the idea here that we're just going to go cosine of k1 L minus theta? This is, let's say it's close to 0. So that means it's almost the same as, right? And we square this, get plus or minus 1. We get, hold on, we square this. So we're going to square it. Oh, excuse me. Minus KL, minus KL, minus 2 KL. T equals 1 minus R. So we cancel off the ones, divide by minus 7, so we have R is equal to Ouch, I shouldn't have done this. I should have just left it the same. Oh. Oh, what's the small angle approximation I'm missing to get this to work? This is our delta E. You guys can see the cat. Hey, put your tail over there. Ah, don't bite me. All right. How can I get this over? So essentially, we've got our circle here, and at these values, we have cosine of inverse cosine of root t is equal to so there's probably some arc cosine. I feel like it's 1 minus theta, like cosine of theta for small theta is equal to 1 minus theta, because we can do that for sine. Maybe that's not true because we're I'm missing a small angle approximation. I don't know which one it is. Should I look it up? No. Here we go. It's not 1 over theta. It is cosine of theta is equal to 1 minus theta squared over 2. So this means K1L minus theta is equal to 1 minus T over T minus 2. And we're going to have plus or minus this, right? So we're going to have plus, hold on a sec. We're going to have minus 2, and then we're going to have K1. We want to go this slight change in the wavelength. Should we change it to it's delta E? I'm just wondering whether we want to substitute that in. Let's go K1L. I'll just do what I have right now, plus epsilon L minus psi equal to 1 plus T minus 2. No, not plus. It's, what is it? This is going to be the same. Ooh. How do I get the... I think it's because I got to take the square root. How am I going to get that gap? Oh, no, this is our cosine. We want the arc cosine. Hold on a second. Let me rewrite the problem. I have cosine of KL plus psi over root T. This is equal to 1. T. So I have 1 minus KL plus psi squared 2. It's equal to root T. So that's our approximation, right? And We want to get root r, right? And so we want to show that this is the energy gap. So we also know, what else do we know? We also know cosine of what is our new k in the energy gap? Good. E plus delta E equal to h bar squared k squared. I think we can just replace this with delta k, right? But now it's no longer delta k is equal to size. It has to be that k plus. So we've got cosine of k plus delta k. It's actually the power fourth though, right? So I think we can just go 1 minus k plus. Oh, how do I get rid of this without having all these terms? Yeah, I'm gonna look it up. Let's see here. So what did they do? All right, Taylor, expand. M pi plus epsilon. We have wow. I'm not sure how, because this is gap energy and this E is not energy is KL. I guess this E is an energy, right? KL. Like this is dimensionless. The dimensions don't seem right for this. All right, I'm gonna have to leave it there. Okay, so I'm going to take a break now. I'm gonna be back in the afternoon, finish off this question, and then if I have a bit more time, I'll start going through maybe some of the exams. Well, we'll see. I've done quite a bit. This was my to-do list. You can see most of it's done. Not perfect. Definitely stuff is still challenging, but I think that there's quite a bit that I understand, so it would be a good time to do an exam, even if it doesn't turn out as well as I would like. And I'm going to just keep working on this this afternoon, and I will be back then.